general equation. I show you like a couple of slides before. And can we do something about this integration here? One thing you can do is to split this integration range, basically supposed to from 0 to infinity. I didn't put these two numbers there. You can split this integration range from 0 to d and from d to infinity. 0 is where the interface is, and d is the thickness of the ion rich layer at the interface. Okay, by doing this, we basically divide this integration to two parts. As first part, you consider as the interfacial contribution, and second part consider as the bulk contribution. And with this assumption, d is much, much smaller than the penetration depth, we can have simplified result for the interfacial contribution and bulk contribution. And if we look at these two equations carefully, and the only alpha dependent term here is this Fresnel transmissivity. And so the interfacial contribution basically is dominated by this. The shape of that is dominated by this Fresnel transmissivity. And same thing for the bulk is dominated by this penetration depth. And here is how this T and lambda looks like around a critical angle. So you would imagine your surface signal will have shape like this red curve, and the bulk signal will have some shape like this blue curve. Okay, and our ultimate goal here is to get the interfacial coverage. Okay, so here are these two equations, the interfacial contribution and bulk contribution. For the real sample, we have fluorescence signal from the both interface and bulk. So then we have two unknown parameters, C, which is scale factor, we can talk about in a minute, and phi, which is the interfacial coverage. And both of them are highly coupled. You can see that in the equation, interfacial contribution. These two are completely coupled. So in order to get the interfacial coverage, you have to decouple these two. How we do that? One way is to have a system which does not have any interfacial signals, like here, the bare interface. We don't have any excess ions at the interface. So then your signal basically is from bulk. Then you only have one unknown parameter here. This is scale factor C. So now let's talk about scale factor C. Scale factor C only depends on the scattering geometry, like what absorber you use, and how close you put detector on top of the sample. It also depends on the element itself, like remember that example I mentioned for the calcium and barium. So different element could have different fluorescence yield. That will lead to different scale factors. But the scale factor does not depend on the location of the element. So which means if we get a scale factor C from reference sample, and if we do not change the scattering geometry, we can put this C back to the real sample. Then we won't have one unknown parameter, which is phi. So then we can get phi out. Okay, here's an example of this technique on the reference sample. And picture on the left is a cross-section of liquid sample cell, X-ray coming in from the right side, and we can measure the reflected beam from the left side. We also have this kind of energy dispositive detector on top of the sample, so we can connect the fluorescent signals at almost 90 degrees from the sample. Okay, the reference sample here are bare interface between dodecane and O-beam chloride solutions. On the right side is the data. So the data shown here basically shows for 3 different samples with different bulk concentrations, we get a very consistent scale factor. This is what it's supposed to be because scale factor does not depend on the bulk concentration. Okay, here's another example. We use this technique for a solvent extraction system. Solvent extraction is a technique to extract some specific metal ions from the aqueous phase to the organic phase with the help of the extractants. And the interfacial structure of this system is very important to understand this process. Here's our model system. We use DHDP as extractant and O-beam chloride as the target metal ion in the aqueous solution. And we did reflectivity on this system. It probably looks familiar to you because we did the X-ray reflectivity analysis on this data yesterday. And it turns out it has like bilayer structure like this. We do expect some metal ions in this structure, but with X-ray reflectivity alone, we do not have direct evidence. So what we did is we did X-ray fluorescence on this system. So first of all, we did a XFNTR for the reference sample, so we can get a scale factor. As you can see, this data has a bulk signal shape. Okay, and we plug in this scale factor from the reference sample to the real sample, then we can get the interfacial coverage of OBIA. We also can get the number ratio between the extractant and ions. So these techniques like X reflectivity and XF and TR are complement to each other. So most of the time, we need multiple techniques to get a better understanding on the interfacial structure.